Hello, everyone. In this section, we will introduce the early effect of bipolar junction transistors, or BJT devices. From the previous section, we know that the collector current, IC, comes from carriers injected from the emitter into the base. These carriers then diffuse across the base region and are collected by the collector, forming the collector current. Therefore, IC is proportional to the carrier concentration gradient in the base region, and it has an exponential relationship with the forward bias of the BE junction. From the ideal equation, IC seems to be independent of VCE. However, once the base width becomes smaller, the situation changes. When the base width becomes very narrow, an increase in VCE can affect the collector current. Since VCE equals VCB plus VBE, and VBE is approximately 0.7 volts and does not change much, VCB increases as VCE increases. This means the reverse bias of the BC junction becomes larger. When the reverse bias of a PN junction increases, the space charge region, or depletion region, becomes wider. As introduced in the previous PN junction bias chapter, the depletion width is proportional to the square root of the reverse bias. A wider depletion region reduces the neutral base width, WB. If WB is much larger than the change in depletion width, the concentration gradient in the base is almost unchanged, so IC is not sensitive to VCE. However, when the base region is already very narrow, the increase in VCB caused by a higher VCE makes the BC junction depletion region wider. As a result, the neutral base width becomes narrower, as shown in the figure. Once WB becomes narrower, the concentration gradient in the base region becomes steeper. A steeper concentration gradient increases the diffusion current, and this finally increases the collector current, IC. Therefore, when a BJT has a very narrow base region, its collector current in active mode becomes related to VCE. A larger VCE causes a larger increase in IC. This gives the IC versus VCE characteristic curves shown in the figure. The blue curve represents a BJT with a wider base. Its IC is not sensitive to VCE and is almost constant. In contrast, for a BJT with a narrow base, IC increases as VCE increases, as shown by the red curve. If we extend the active mode IC curves for different VBE values back to the x-axis, they intersect at the same voltage, negative VA. This voltage VA is called the early voltage. Next, we analyze how the early effect modifies the collector current equation. As shown in the IC versus VCE characteristic curve, let us use an operating point with the bias conditions VBE5 and VCE5 as an example. In the ideal case, when an NPN BJT operates in active mode without the early effect, the IC current is represented by the blue curve. The ideal current is labeled IC5 double prime. It equals IS multiplied by the exponential of VBE5 over VT. Here, the ratio VBE5 divided by VT is inside the exponential term. In this expression, IS is the ideal saturation current coefficient without the early effect. When the early effect is considered, the red curve gives the actual current value, IC5. From the graph, IC5 equals IC5 prime plus the extrapolated line slope, IC5 prime divided by VA multiplied by VCE5. Here, IC5 prime is the current, where the active region line is extrapolated to the y-axis. If we factor out IC5 prime, we obtain IC5 equals IC5 prime multiplied by the quantity 1 plus VCE5 divided by VA. Because VA is usually tens of volts, it is very large, so the extrapolated line slope is small. From the graph, when VA is large, IC5 prime is approximately equal to IC5 double prime. IC5 double prime is the ideal collector current without the early effect, and it equals IS multiplied by the exponential of VBE5 over VT. Substituting this back into the equation gives IC5 equals IS times the exponential of VBE5 over VT, multiplied by the quantity 1 plus VCE5 over VA. Finally, we obtain the collector current equation of a BJT with the early effect. IC equals IS multiplied by the exponential of VBE over VT, then multiplied by the quantity 1 plus VCE over VA. In this equation, VBE over VT is inside the exponential term, and the second bracket, 1 plus VCE over VA, is the early effect correction term. Here, IS is the ideal IS without the early effect. Now let us look more carefully at this collector current equation with the early effect. As shown on the slide, IC5 equals IS times the exponential of VBE5 over VT, multiplied by the quantity 1 plus VCE5 over VA. The first part, Is times the exponential of VBE5 over VT, is the collector current without the early effect, which is labeled IC5 double prime. Therefore, IC5 can be written as IC5 double prime multiplied by the quantity 1 plus VCE5 over VA. If we distribute IC5 double prime into the bracket, we obtain IC5 equals IC5 double prime plus IC5 double prime divided by VA multiplied by VCE5. Since IC5 prime is approximately equal to IC5 double prime, IC5 double prime divided by VA is approximately equal to IC5 prime divided by VA. This value is the slope of the extrapolated dashed line. We define this slope as 1 over RO. Therefore, IC5 equals IC5 double prime plus VCE5 divided by RO. The parameter RO is the equivalent resistance that represents the extra collector current caused by increasing VCE under the early effect. The equivalent circuit of an NPN BJT can be described as shown on the slide. The upper circuit is the equivalent circuit without the early effect. The base emitter junction is modeled as a forward bias diode, and the collector current IC is determined by VBE. It equals Is times the exponential of VBE over VT, which is labeled IC double prime. When the early effect occurs, the collector current increases from IC double prime by an additional term, VCE divided by RO. In the equivalent circuit, this additional current can be modeled by placing a resistor RO between the collector and emitter. Then the total collector current becomes IC double prime plus VCE over RO. Therefore, in the equivalent circuit, the early effect appears as the RO effect. This output resistance RO equals VA divided by IC prime and is approximately VA divided by IC. Therefore, RO is proportional to the early voltage, VA. So with the early effect, the collector current equals the original ideal collector current, Is times the exponential of VBE over VT, plus the additional current delta IC, where delta IC equals VCE divided by RO. When VA is infinite, RO is also infinite, so the additional current becomes 0. This corresponds to the ideal case with no early effect. Therefore, a larger VA means a weaker early effect in the device. This concludes the introduction to the early effect of bipolar junction transistors, or BJT devices. Please look forward to the next lecture. See you next time. Bye.